So yeah, as I said, we're going to look at Spalart-Allmarus model and look at the original paper and some of the biographies and motivation development. And it's actually a four-part model construction. And it's not like a direct derivation. It was like a construction of an eddy viscosity type model. And it's a one-equation model, as I mentioned. And it was inspired by a lot of the previous efforts, including the work of Baldwin and Barth, which I mentioned last time. So let's just look at the major things. I'll try and hit the major points, and we'll look at the paper itself maybe Tuesday near the end of class. So here's the cover page. You can see it was presented as a conference paper, and both the authors were associated with Boeing Commercial Aircraft in Seattle, Washington. Today they still have an excellent CFD group. One of my undergrad researchers was actually placed there. I'm very proud of him, directly into the group. And they're still there today, well known, extremely well respected. Spalart is still, at the time of today, at Boeing as a technical fellow, which is probably the highest technical position you can get in a company like that. And Allmarus is actually working directly for MIT as a researcher for the past number of years, but he also sits out, last time I checked, in Seattle. And they're both active in the AAA. So if you go to AAA conferences like SciTech or Aviation in the summer, you'll probably run into them. And I think near the end of the class, I also want to sit with you and watch a video of Spalart talking about the differences between LES, DNS, and RANS. And it's a really great lecture I found recorded. So we might watch that at the end to also give me a break. So there's the cover page, and this is the first time it was laid down, and this was converted into a journal article, which I put in the reading online. And I reached out to Allmarus, and I didn't think he had a picture to share publicly, so I won't put one in a recording. But this is an official portrait of Philippe Spalart, and this is a little bit later. This is more recent. But there he is. And I asked for a quick bio from Allmarus through an email, and he wrote back. He got his BS at Washington and Ph.D. MIT, 22 years at Boeing, and 10 years at MIT. And lately he's still working on CFD and RANS, and moved into high order methods and stability for finite element methods and adaptive gridding, which are hard problems. And here's an official bio from online that I copied and pasted. Spalart studied math, physics, engineering in Paris, obtained a PhD at Stanford, NASA, Ames in '82. It's 39 years ago. He's still at the Ames area. While he was at Ames, he conducted extensive DNS, transitional turbulent flows, moved to Boeing in '90, created this one equation model, and wrote reviews and co-holds patents on many things. And he also proposed a new concept called DES, detached eddy simulation. And that's actually a blend where you take maybe the best things from LES and the best things from RANS and combine them. So where you might have more steady turbulent flow, you would have a RANS model, and in unsteady or separated parts, you would have like an LES model, and it all works together seamlessly. In fact, my first master's project was doing detached eddy simulation for wind turbine airfoils. So I quickly got acquainted with that method. But there's lots of this DES method. It's like a hybrid method. So that's the major background of the contributors. And let's look at some of the notes, kind of mixed notes from papers and things. And some of this is motivational, like why would you create a new model? And it's for a lot of reasons, and we'll note some of them first. So first of all, like in AAA and the whole aerospace community, there was a need for, and I guess funds to invest in a new generation of turbulence models, mainly in one equation and two equation approaches. And one of the problems with the previous models we looked at is they really depend on like having orthogonal grids or structured grids. And there was a big push to try and not only improve the models for predicting separation, but also to try and create models which can run on unstructured grids. Because of course, if you want to have a one equation model to predict the aerodynamics over a full aircraft, which was like a goal of this type of model, you would have an unstructured grid. You know, it takes a lot of time to create a structured grid over a simple airfoil, let alone something like landing gear or fuselage and wings and nacelles. So a few little tidbits is the Baldwin-Lomax model. Made like Navier-Stokes calculations possible, but NCS needed structured grids for ease of implementation. So from the get-go, this was a goal to overcome. And the Johnson and King model, which we also reviewed, I'll just call it J-K, fulfilled some of the issues with predicting shock boundary layer interaction, but unfortunately relied on structured solvers. So those are problems. And part of these issues with these codes is they were called non-local formulations, which could be good or bad depending on what you want to do, but if you have an unstructured grid, it's much harder to make a non-local formulation. It's also shown that unstructured solvers were becoming way more common in the community for the reasons I just noted about complex geometry. And we needed to push these 1 and 2 equation models in that direction. And there's a great example, like if you just have a C grid, and that would be like an airfoil, and you have a grid that goes around like this. So there's the grid. This is the airfoil in the middle, and there's a grid that's this way. And it's a structured grid, right? So if we unwrap this, we have a structured grid. Very coarse. Can unwrap that and just have a single structured grid, right? Just like we do in our class project. We would have transforms and turn it into a computational domain with even, delta, eta, delta psi. There's this boundary here, right? So this boundary here is just one where flow needs to go from one side to the other and be continuous, especially if it's a subsonic flow with no shocks. So that boundary there is a problem for some of the earlier models, because the way the earlier models were formulated, the eddy viscosity, nu tau, became non-continuous along boundaries of structured grids. And it should definitely be a continuous quantity. So that's because these formulations, well, that's just turned out how to be, and there's a lot of reasons for that in the formulations. And so these were like certain problems were identified and motivated the work. And here's some of the things noted also. The models for K epsilon, higher order models are usually local, and they might have non-local wall terms, like 2-point correlations, and those were harder to program on unstructured grids. So those were all the other motivations that Spalart-Allmarus noted in their work. They also had some criticism on 2 equation models and the Baldwin-Barth model, which we just talked about as a 1 equation transport model derived from K epsilon, right? So that's from K epsilon derivation. And I think they probably looked at that approach and thought, well, we could also take K epsilon and combine them in some way and create a transport model for like Reynolds, turbulent Reynolds number, like Baldwin-Barth, but they didn't do that. They thought a little differently. And they also thought that maybe 2 equation models would be 1 well, more expensive, but maybe not as useful and numerically unstable. So those were reasons they might stay away. They did see some advantages for these approaches, as you'll see today, for predicting shock boundary layer interaction. And they're definitely superior for massive separation problems. If you have a bluff body or a wake of an aircraft. But unfortunately, they required finer grids near the wall. And that was seen as a problem. And you might say, well, I could just use wall functions, right? Like we do in some codes today. But if a flow separates, then your wall functions are kind of useless. Because using a wall function, you're assuming that the flow is sort of fully turbulent and attached. And if the flow separates or goes into a wake region, your whole wall function scheme breaks down. And it was a big motivation to try and create a model that had, you know, not much greater cost relative to the algebraic models. And algebraic models don't require such a refined grid near the wall like K epsilon and K omega models, which we'll talk about in the future. So as I noted here, these types of models in practice, especially early on, required wall functions, and then all that wonderful physics in the two-equation model wouldn't have been used because you're imposing a solution that doesn't allow separation or even transition. So those are just some quick thoughts about it. So then they kind of looked at this Baldwin-Barf model. It's quite inspirational. And as I mentioned, it was actually given to Spalart as a reviewer at NASA. And I think this is one reason he's a proponent of one-equation models. And I remember in one lecture he gave at AIAA, he said, of course I'm going to make a one-equation model. I think it's partly a joke, because he's a big proponent and built his career around it. And what he liked about this model, and probably inspired future models, is, of course, it's a one-equation model, as you know, for Reynolds, turbulent Reynolds number transport model. And it's derived from K epsilon. And it had other good things, but it wasn't, of course, eddy viscosity. It was RET. And RET isn't a very common one-equation model, and it's definitely not something that's maybe as physical like eddy viscosity. Eddy viscosity is something we just understand. You add it to your viscosity as like a penalty for the flow in the momentum equation to kind of model another state of the fluid as if it was turbulent. So the bottom line in this model, which was inspired by Baldwin and Barf's work, which we discussed last time, and maybe some of the shortcomings of K epsilon models that they perceived, and that's their opinion, right? Other people are big proponents of K omega, like D.C. Wilcox and Andre Komogrov and those types, is sort of find this intermediate ground for large-scale computations on structured grids. So, let's see here, go down here. So what they want is allow for a semi-local, that's their terminology, formulation near the wall. And this is just maybe just a philosophical point of view. They wanted to develop a model that had same properties as the Baldwin-Barf model, in terms of compatibility. And it would work with unstructured grids. And it would be more accurate away from the wall, which wasn't always true in earlier models, but they cared most about boundary layers. And a lot of the earlier models were calibrated only for boundary layers, maybe with shocks and maybe separation, but they also wanted to seamlessly handle wakes and multiple shear layers, and way more complicated physics that you just can't maybe imagine in advance, like an aircraft company would want to handle. And I should note that there's a paper that at least kind of motivated them beyond Baldwin-Barth model, and it's by Ni, Karaz, and this, I think, was an incompressible model. Oops, sorry. And this is mentioned very briefly in their paper, and I have not reviewed this model myself. It's probably something on my to-do list to check out. Also, they noted the claim, or the common claim, that one equation models are incomplete because they often have some calculation like every grid point's distance to the wall. And you'll see that the Spalart-Allmarus model uses that, especially for transition. So those are the goals, big goals. And when you have a big list like that, I think that's pretty intimidating. And they spend a lot of time in the community out at NASA Ames and working with them, the senior people, to try and formulate those. And they were inspired by a lot of models, and they had access to all the best data and DNS insight. So it took them years of their research time to develop the physical insight and mathematical abilities. I should also note they want it to be numerically stable and behaved. And it's easy to write down equations, and then when you run them through your CFD program, you'll get bad behavior like negative viscosities and things. And so when they were formulating some of these terms, which we'll note in this class and in the next one, they often mention it's chosen partly just to have like positive values or well-behaved solvers. So all the choices are not just for physics. It's also to have a well-behaved solvers. So in their thinking, I think they set out to create their model in 4 parts, and that's how they presented their original paper. Not their journal articles or anything after, but that's why I think it's such an interesting paper, because you can sit down and see how 2 people came together to do something that hadn't been done before. That's pretty cool. So they noted that they created their model in 4 parts. And the first one is sort of just for free shear flows and layers. And it's probably the most direct model. And then they took that model and modified it, and by adding and modifying terms in the model so that they could handle high Reynolds number flows near the wall. And then the third step was to modify the model again to handle low Reynolds number flow near the wall. That's basically the viscous region. And then the fourth part of the modeling was to try and put in some transitional effects so you can predict transition beyond what was done earlier. And just to note, earlier transition models were just basically having the eddy viscosity be forced to be 0 in some point. So their strategy was to add in a source term. So we're going to try and look at these 4 parts independently. And in their nomenclature, which is sometimes repeated here, is there's like a common subscript for each stage, e.g. CB1. So the 1 is from first modeling stage, as an example. So you'll see subscripts like 1, 2, 3, 4, and that just denotes if the constant or function is from which part of the stage. So today, I don't think you'd have their fourth part of this model, which is transitional. Later on, people and the original authors put in better transitional models and source terms. So really the first three stages are the most important, especially the first one, because it's like the base model. Okay. And another reason they did this is so that they can criticize the theory as it's developed, and for the reviewers at NASA and other organizations to criticize it piece by piece. And I think that was a good strategy to communicate with the community. By breaking it down in pieces, they, of course, had a shorter step to creating a model and validating it, but it also let people understand its construction piece by piece. And I haven't seen many people use this approach, but I think it was part of the reason of this model being accepted. And also, their aim is always to try and create a complete model, but I do argue myself, it's my opinion, that it's, not complete due to wall distance functions. So, like previous authors, they chose to do an eddy viscosity model, and they denote that by V sub I. And then they define a Reynolds stress. So Reynolds stress from the Rand's equations is UI uj bar, and they're dropping primes on their subscripts with little u's and big U's. So little u's are fluctuating variables, big U's are mean variables. Here's our strain rate tensor standard definition. Partial ui, partial xj, plus partial uj, partial xi. So that's pretty straightforward definitions. And they note right away that unlike Baldwin-Barth and two equation models are not tracking turbulent kinetic energy K. So they really have no information about K, but they're critical of that. And they're critical of the Boussinesq and eddy viscosity models that might use a turbulent energy equation, like in a one equation model. And they argue that in those other models, they're all inaccurate. Because they incorporate 2k over 3 in the diagonal stress term, which is an approximation. Okay. And this is based on their own DNS simulations from NASA Ames. And they reference these in their paper. In one equation models, there's zero equation models which have, of course, an eddy viscosity, but not turbulent kinetic energy. They can obtain a rough approximation of K by just saying, okay, it's going something proportional to nu times Sij, and it's diagonal. So, okay. That's fine, but then these models would require that the Reynolds stress tensor to be positive definite. And if you look at that tensor, then you'll find that the eigenvalues are basically, let's see, k over 3, turbulent kinetic energy over 3, 2k over 3, and k. And of course, none are close to 0. And this is just general trends for most of the engineering-based flows they look at. Likewise, in eddy viscosity models, then these same eigenvalues in the tensor for eddy viscosity model will be as something like square root of 2 nu t square root of Sij over 3 times a constant. And, well, you have 2 of these. Okay. Leave that there, sorry, going too fast. Now, in free shear flows, which is what's examined first in their first modeling effort, I guess I should put an underline there, or a box, because it's moving into the first model. It turns out for eddy viscosity, there's no exact transport equation. Right, so it's not like we can take our equations of motion and directly form an eddy viscosity model. But this is something that would have to be constructed maybe in a semi-empirical way or an ad hoc way for just a turbulence closure. So since they can't like directly derive an eddy viscosity model, they wanted to form it term by term. And it's often that models, almost all the ones we talked about, are calibrated against homogeneous turbulent flows, but they decided not to. And the main reason for that is it's very rare that you would be running your model against a purely homogeneous isotropic flow anyway, unless you're in like grid turbulence in a wind tunnel. So what they did is form a model with basically a diffusion term, no destruction term directly, and see what that looked. So what they did is try and construct a model directly from mean flow quantities and eddy viscosity and try and build a transport equation. So just to write a transport equation for nu t. And then they basically invoke common themes or equations from past models and experience. So you have a left-hand side and a right-hand side of a transport equation for eddy viscosity. The left-hand side can be written as a material derivative, partial Vt, partial T plus Ui, that's the mean flow UVW, partial Vt, partial Xi. So that's the left-hand side. So that's just sort of the easiest choice because all the equations sort of look like that. Then the right-hand side could be like previous models. You got sources, you got sinks, you got production, diffusion, destruction. But we're only going to write a model, like a base model, the first model, which is for sort of like free shear layer turbulence. And so for those flows, the dominant terms are going to be a production term and the diffusion of the turbulence. So the first step is to form a model for the production, and the second step will be forming a model for diffusion. And once you do that, then you can write a single eddy viscosity transport equation, which is the basis of all Spalart-Allmarus based one equation models. So for the production term, it's a little bit straightforward, and they looked at and said, well, it should be some function involving partial u, partial x. Why? Because in a free shear layer, you have shearing of a fluid, and that should be producing turbulence, hopefully. Where does that occur? Shear layers, jets, and boundary layers, of course. So it's pretty dominant. Okay. And sorry about that. I'm going to get my place in my notes and not just talk. Okay, so one thing they note is nu t is a scalar. And there's going to be a new variable, which makes their model unique, s. And s is a scalar norm of mu I, which is like a eddy viscosity vector. Now, if we take s times nu t, we're going to get that as a possible variable in the production term. They also introduce vorticity, omega, and write it as the square root of omega ij, square root, sorry. And other things they're going to introduce is strain rate, 2Sij, Sij. These are all variables we'll need. And they assume that turbulence is found only where vorticity occurs. So that's one of the early assumptions of their model that I note. And I think it's noted later on in their other papers that it is possible for vorticity to form in flows where it's not really turbulent. One case would be behind shock waves. So in region, there could be vortices behind shocks, and the vorticity is pretty weak and doesn't produce much eddy viscosity. So it's sort of an okay assumption. But if you have like a curved shock, there's a flow, there's induced vorticity, and that could be a problem in their early models. But it's not a big problem because it turns out the eddy viscosity here doesn't increase too much. So just based on some of these arguments, they proposed a production term. So this is their left-hand side, which we noted up here. And this is the right-hand side. And that's their production. CB1 is a constant coefficient. So that's a calibration coefficient they introduced. They're just saying, hey, this transport eddy viscosity goes as S times nu t. And S is this what they call the scalar norm in the model. Nu t is eddy viscosity, of course. Subscript B stands for basic because it's for the basic first model. Subscript 1 means it's from the first part of creating the model. Okay, so that's a strong statement, and you can see it's not done with some big mathematical rigor. I think it was written down with a lot of physical insight of how to create a one-equation eddy viscosity model. So maybe it's a bit of hand-waving in the turbulence community, the dark art of turbulence. Just using this model, it would be horrible for many flows, including homogeneous turbulence. So you wouldn't want to use it for that. For isotropic turbulence, you would have something like d nu t, dt is 0, as s is 0 in isotropic turbulence. And in isotropic turbulence, it's from the book on Inhomogeneous isotropic turbulence. We know that the turbulent kinetic energy will decay as time to the -6/5 power. So that's a little note for future calibration. And this means that the simplest combination will have the same dimensions as Vt, where epsilon is dissipation in this flow, which decays as, let's see, t to the negative 1 over 5 time. So this means in anisotropic flows, mu I can only increase under the effect of production in a manner that depends on the choice of S, my scalar norm. And they're going to look at this choice of S in later parts of their model, but this statement here is just seen as the classical behavior of shear flows. And they calibrated just this simple model by running it with continuity, momentum, energy, and this closure with this single coefficient, and they found that CB1 should be about 0.135 for all shear flows. So a super simple model works for all shear flows. But then, a free shear flow. It wouldn't work for boundary layers, because boundary layers and shear layers are two different flows. Now, this model only has a production term, and a diffusion term needs to be added to it. So that's the next step in our model. So we're looking for a diffusion term, which we would add here, right? So we need to add diffusion term. That's the next step of part 1. And you can kind of see in 556 we got what we'll find. But in classical diffusion operators, how did they find a diffusion term for eddy viscosity? Well, they just looked at past models. And past models used something like nabla dot mu t divided by the Prandtl number of nabla nu t. So that's the form. And this is the turbulent Prandtl number. And I'm using their notation. A lot of times I write PR sub t for turbulent Prandtl number. And usually that's 0.90 in most of these flows. So they want to try and create a conservation integral for nu, which is compatible. But there's really no reason that nu should be conserved as a variable. I mean, because they don't have other terms in the model so far. And they also noticed that other people who manipulated two equation models would try and bring out these diffusion terms, and they're not conserved in those models. So what they argued is they wrote that by analogy, they allow a non-conservative diffusion term involving the first derivative of nu, turbulent. So this is their next step after making these arguments. There's no rigorous mathematical definition. These are the prime arguments they made in their core paper. And this is what they call their basic model, where all the other Spalart-Allmarus eddy viscosity type models come from. So we already talked about the left-hand side, right? That's just partial nu t plus u partial nu t partial xj. Material derivative. This is your production term again. And then this, of course, is your diffusion term. You have another maybe 5 or 8 minutes in class, so we'll keep going. And you'll notice here they introduce a second coefficient. Besides this coefficient here, which is the PRT, turbulent Prandtl number. So I'm going to make just two major points about this model. The first is that it's not consistent with isotropic turbulence. Like in wakes right now. And this could be a problem in shear flows in which UT might decrease to negative values, which would be totally unphysical, and so it's not a model you would want to use in general in practice, and so we need to do more things to it to correct this problem. And another problem pointed out was that this diffusion term as proposed could give very low unphysical values of mu, which is also bad. And it turns out that they make some notes about calibration of CB2 just for free shear layers. So they're not running against these flows to calibrate CB2 because they got to add more terms on the right-hand side to correct these problems. But they found CB2, and I'll write it in a different color, to match experiments and like low Reynolds number DNS, I guess, is absolutely less than or equal to 1, but of course positive. So it has not a really well-defined value yet. So that should be calibrated a little bit more later. So that was our first observation. And so they say, well, we need to try and do something to calibrate CB2 because shear layers are giving it a wide range of values. So we need to look at another basic flow to calibrate CB2. So there's a choice, a big choice. You could look at other things that are maybe more important to you, like boundary layers, right? Because ultimately there's a boundary layer on every aerospace device. What they did instead was look at a turbulent front. So I'll introduce this here, and we'll talk about it and probably end after we calibrate this coefficient. So here's a flow. This is a turbulent front. And there's turbulence behind it. Now just put a bunch of dots. This is very cartoonish, isn't it? And out here is just a basic laminar flow. So there's a case where you have a laminar flow, there's a quick transition like a turbulent front. And these are measurements that can be conducted. And if you look at a flow like this, you can actually take this equation and try and seek, if you impose values like density, velocities, energies across this type of system, then you can try and solve the transport equation for eddy viscosity, and it should have a form that looks like this. So that's what they did, and this was a well-known thing before they started the work. This isn't their original work. But they showed eddy viscosity should go as something like, well, it should always be positive, so they put a max in here of like some type of constant A times X, which is this direction, times X plus A, 1 plus CB2 over the turbulent Prandtl number times time, because there's like a decay of this little fluid parcel going this direction. So X and T are related. And this is what they call a linear ramp function, because it's linear. And they made a few observations about it. First, if CB2 is greater than -1, then the parcel will propagate into the region, which is physically a crux. And that's really important because that way it corresponds to the solution. They looked at other models and that applied this. They took the Baldwin-Barth model, and they applied the Baldwin-Barth model and also find equivalent eddy viscosity, and found that CB2 equivalently would be to -2, which is unphysical. So the Baldwin-Barth model, if you applied it, wouldn't be able to work. If you choose values, of course, between, say, -1 less than CB2 is less than 1 for this problem, then they're still getting solutions which look like experiments. So at least they had a bounded range for this based on this experiments and this analysis. So it's 1:38 here. So what I propose is that we kind of stop here and then come back and try and finish the calibration of CB2. And then on Tuesday, we'll try and complete steps 2 and 3 of the Spalart model, and then we'll look at results, okay? So thanks for your time today.